Hello my scholars, you're welcome to my school YouTube channel. My name is Emmanuel and in today's video we'll be tackling JAMB CBT past question for chemistry in the year 2024. Please don't go anywhere, stick around and we'll be right back. You're welcome back to my school YouTube channel. In today's video, we'll be tackling question 101 to 125. Now let's move on to question 101. The general molecular formula CnH2n-2 represents that of an what? Alkyne, alkene, alkane, and alkyne. Let's move on to the board and see all hydrocarbons, okay? We can have them as alkane. They are classified as alkane. We have those ones that are alkene, okay, E-N-E, and those that are alkyne, okay. This saturated hydrocarbon, the alkanes are the saturated hydrocarbons, the alkene are unsaturated hydrocarbons, and then the alkyne are also unsaturated hydrocarbon because of their double bond and their triple bond respectively. So for the alkane, they have the general formula CnH2n plus 2, where n can be from 1, 2, and so on. So for the alkene, we have CnH2n, just that. So from n has to start with 2, number 2, because the first member C1H, if it were 1, C1H 2 times 1 does not exist because carbon should have a bond that is 4, okay, in number. So the number of carbon here should start from 2, not 1. And then the alkyne has the general formula CnH2n minus 2, okay. So the question says that the general molecular formula CnH2n minus 2 represents that of and what? Of an alkyne, okay. So let's move to the screen now. Option A say alkyne, B alkene, alkane, and alkanal. So the general formula for alkanal actually is CnH2n plus 1 OH. Okay, so the correct answer here is option A, alkyne. Question 102. What accounts for the low melting and boiling points of covalent molecules? Usually we know that covalent molecules are molecules that are formed when atoms or molecules of a particular element or another element actually share electrons together, okay. Molecules that are formed are called covalent molecules, but because the intermolecular force, okay, between them that binds those atoms together are very weak, okay, so it requires just little amount of energy to be able to break up that bond because it is just weak intermolecular forces that actually bind those molecules together. So as a result of that, there's going to be lower melting point or boiling point of those kind of molecules because little amount of energy is actually required from there. So the question says, what accounts for the low melting and boiling points of covalent molecules? Option A says they have weak intermolecular forces. Yes, binding them together. Option B, they are three-dimensional structures. Yes, they are, but that will only show us what the structure is, not the low melting and boiling point. They have definite shapes. Yes, they do. Okay, and then we have possessing shared electron pairs, but that does not account for low melting. What shows what is responsible for their low melting and low boiling point of those covalent molecules is because they are held together by weak intermolecular forces, okay, force of attraction between them. So because of that, it requires little amount of energy to be able to break those bonds. So the correct answer is option A. They have weak intermolecular forces. Question 103. After breathing in a test tube that contains acidified K2Cl2O7, a man noticed the change in the color of K2Cl2O7 from orange to green. This suggests the presence of what? What actually happens is that what? Oxidation has taken place, okay? The initial color of K2Cl2O7 is actually purple. It's actually orange in color, okay? So, but once it is brought, the man breathed into it and then the color changed from what? From orange to green. It means that oxidation has taken place. What actually happened is that what? Cl2O7, the ion here, Cl2O7 2 minus has actually been reduced to Cl3+. Okay, there is reduction that has taken place from Cl2O7 2-, okay, to +3. It has been reduced because there's been increase in oxidation number, so it has been oxidized. Oxidation has taken place. Okay, so because of that, it has shown that possibly or most likely the man actually had taken or consumed food that is filled with alcohol, okay, that has alcohol content in it. So it is alcohol that actually oxidizes in the presence of H2SO4. Okay, that is what happens. So once it is brought there, it will now oxidize the color of that K2Cl2O7 from orange to green. So it is the presence of nothing else but alcohol. We call it oxidation of that. So alkanol, option A. Option B is alkanal. Option C is alkanol and alkanoic acid. So the correct answer is option C. Now let's move on to question number 104. Hydrochloric acid is not suitable in the preparation of ethanoic acid because it's what? Yes, we know that hydrochloric acid is a strong acid. Yes, it has a basicity of 1 because the number of hydrogen, replaceable hydrogen ion that is here is just 1. So H plus by the time you write dissociation of this. So if you dissociate this in water, it's going to dissociate completely. Okay, but the challenge with this hydrochloric acid, why it cannot be used in the preparation of ethanoic acid, is because it is volatile. If you try to react it or subject it to it, it will evaporate so fast, and then you will not be able to get what the quantity of ethanoic acid that you need. Option A says it is too acidic. Well, it is acidic. If it is too acidic, I think that should be good reason why we can be able to use it to prepare ethanoic acid, because this is a weak acid. Okay, strong acid can be used to prepare weak acid. Okay, so this is not a reason why, or a suitable reason why this is not suitable for ethanoic acid preparation. Okay, option B says it's too volatile. It is too volatile because if you apply it or you try to react it, what happens? It will evaporate so fast, you know, that you will not be able to get the quantity, the ethanoic acid that you intended what producing at the end of the day. Option C says can attack cork and rubber used as containers. That's not true, even though it's a strong acid. Okay, but that will not make it not suitable for ethanoic acid. If it is that, then we can get something else as a, you know, as to cover the container, in which if it can attack you know, the cork and the rubber, we can use some other, maybe some borosilicate glasses or something we can use that will not attack it. So this is not reason for that. Option D says turns blue litmus red. Of course, we know that all acids will turn blue litmus into red to show that they are what? They are acidic in nature. So the correct answer, the reason hydrochloric acid is not suitable in the preparation of ethanoic acid is because it is too volatile. It is highly volatile. It can evaporate on time. So the correct answer is option B. Now let's move on to question 105. A radioactive element of mass 1 gram has half-life of 2 minutes. What fraction of the substance would have disintegrated after 10 minutes? Now, at the beginning of the reaction, don't forget radioactivity has to do with what? A spontaneous disintegration, okay, splitting of a particular atom of element or nucleus of an element, and then you form either a new element, atom of another element eventually along the way, or it can take some time. But we are talking about half-life here. Half-life is the time it's going to take for half of the whole mass of a particular atom or neutron to do what? To disintegrate, to split into half. Okay, so if the whole mass, the entire mass, okay, of that element is 1 gram, and it's going to take half-life of that 1 gram to split, it's going to take 2 minutes for it to split into half. Okay, now what fraction of the substance would have disintegrated after 10 minutes? So after 10 minutes now, what amount of this will be left remaining? That is what we want to calculate. So let's move on to the board and see how to go about that question. So we're told that the radioactive element of mass 1 gram, so which means that the entire mass, we say original mass is equal to 1 gram. Okay, also we're given half-life. We represent half-life with T, half this way, was given to be 2 minutes. Okay, was given to be 2 minutes. Then we have to find what fraction of the substance would have disintegrated Okay, so we call that residual. Which one will remain? Residual mass. Okay, that will remain, question mark, after 10 minutes. So that 10 minutes is what we call the exposure time. Exposure time is 10 minutes. Okay, since both of them are actually in the same unit, we have 2 minutes, we have 10 minutes, so there's no point doing any conversion. So we just work with that. So what is the formula? The formula to find this is, we say residual mass. This is so easy. Like I said in one of our video lessons, we said there are different formulas, you know, of solving this. Even in your physics, okay, there's another approach you can use, but this, you know, is kind of so easy, and then you don't need to cram it. So residual mass, which you want to find, will be equal to original mass, that's the entire mass that was given, all over 2 raised to power n. I think this is so easy to remember. Residual mass equal to original mass divided by 2 raised to power n. But what we need to find now is this n. Don't forget, n is what we call the number of activity. Number of activity is n, and what does it represent? It is equal to exposure time. Exposure time, the time is going to take for the residual mass to remain, divided by half-life. So that is all. So we can find what n is here. N is equal to exposure time is given as 10 minutes divided by the half-life was given as 2 minutes. So by the time you divide this, 2 goes here 1, 2 here 5. So that means the n is 5. So we can come back and then insert this into this place. Now, so we can say residual mass of the radioactive element is actually equal to the original mass was given to be 1 gram. That was what it started with before it started disintegrating, divided by 2 raised to power n. N is already going to be 5. Okay, so that will be equal to 1 over 2 to the power of 5. In the maths means 2 times 2 times 2 times 2 times 2 times 2. So that's going to give us 32. Okay, 2 to the power 5 is 32. So 1 over 32 is what we should have. So after 10 minutes, this 1 gram would have disintegrated, okay, by every 2 minutes would have disintegrated into 1 over 32. So let's move on to the screen and see if we have that in our options. So option A says 1 over 4, option B says 1 over 8, option C says 1 over 16, and option D says 1 over 32. So the correct answer is option D. Now let's move on to question 106. Question 106. Hydrogen chloride gas and ammonia can be used to demonstrate the fountain experiment because they are what? Now, the fountain experiment is an experiment that helps to demonstrate the level of dissolution, how gases, okay, can get dissolved in water. Okay, that's what the fountain experiment is all about. So, if we are looking at hydrogen gas and ammonia gas, okay, it can be used. If you know what experiment, the fountain experiment is all about, I think this question is so easy now. Okay, fountain experiment helps to demonstrate the level of dissolution, solubility of gases, okay, in water. How can they dissolve in water? So option A says light. No. Volatile, is it volatile? Does it evaporate when you add them? Hydrogen chloride and ammonia gas are not that. Yes. This can evaporate, so even if you open this one, it can react so easily, but it is not the reason why we use them to demonstrate the fountain experiment. It is because both of them have a characteristics of ability to dissolve, to be soluble. They are soluble in water. Option C says very soluble in water. Yes, more likely. Option D says heavy gases. No. So the correct answer here is option C, very soluble in water. Now question number 107. In the conductance of aqueous copper sulfate solution, the current carriers are the what? Now, in the copper sulfate solution, when it dissociates, okay, in water, what happens? There will be ions that will be released. Of course, if you dissociate this copper sulfate, let's see what happens in dissociation. If you have CuSO4, if it dissociates, okay, dissociate this, we are going to have Cu2+, okay, copper ion, and then we have SO4 2 minus. Okay, these are ions that will be dissolved. Okay, so once it dissociates in water, you are going to have the metallic ion separated, and then you have this also, this ion that is separated at this point. So this is the radical, we call it sulfate, okay, and then this is what? The metallic ion. So this will dissociate in it, this dissociate. Now these ions that dissociate are what carry the current, okay. When you now electrify it, when you supply electricity into that, what happens? It is the metallic ions now that will now carry, they are the carriers of the current that is flowing in that cell, particular cell. So the question says, in the conductance of aqueous copper sulfate solution, the current carriers are the mobile electrons. No, we are not talking about mobile electrons in the case of this, because once this dissociates in water, we have metallic ions, okay, that are released, okay. Option B says metallic ions, yes. Option C says hydrated ions. Well, hydrated ions would have been because they are dissociated in water, but because the strong one in it is the copper. Copper ion is what is dissociated, and you know generally that copper are metals. Copper salts, okay, are for metallic salt, and metals we know that they are conductors. They are good conductors of heat and electricity, okay. So this is not the answer option. This is hydrated electrons. So the correct answer here is option B, metallic ions. Now let's move on to question 108. A type of isomerism that ClCH double bond CHCl can exhibit is what? Is it chain? Is it positional? Is it functional group? Is it optical? If you look at this, we have a carbon-carbon bond here, double bond here, okay, and then we have a Cl. Let's draw the structure of this so we can understand it better. We have Cl, okay, CH, double bond, carbon, hydrogen, Cl. So if you draw this, you are going to have, this is carbon, carbon, we draw that double bond. We have this, then this is one hydrogen here, and then we have Cl attached to it, Cl. So the same thing, we have Cl can be here, then we have hydrogen here, okay. Now this can exhibit isomerism, okay, because of course if you draw this now, we call this one, because both of them, the functional groups we have here, the substrate groups are actually Cl and Cl, okay. So they are all on one side, so we can call it cis, okay. We have the cis and then the trans, okay. This is cis. We have how many chlorine here? That is 1 2 dichloro. How many carbon we have there? And the 13, that is chloroethene, okay. Cis 1 2 dichloroethene, and then you can change this also to be in this form, carbon carbon. We can have one Cl here and then the other Cl here, hydrogen hydrogen at this point. This you can see them in transcendent order. So if you look at this, we call it trans, okay. One, of course, carbon 1, carbon 2, 1 2 dichloroethene, because we have 2 carbon double bond here, so that's why we have 18. So this is transis and trans. So this is and trans are possible isomers because there is a change in the position of the chlorine. Both of them were up before, and now one is here and the other one is down in this point now. So there is a change in the positioning of the chlorine that we have there. So look at the option again on the screen. A type of isomerism that ClCH can exhibit is not chain, is positional, because there's a change in the rotation of the chlorine. The substituent group that is there was changed. Not functional group, because if it were a functional group, we would have had maybe one of them was Cl, then the other one would be OH, okay, they'll be changed, but the functional group is not changed. The optical has to do with what we call mirror images, okay, like we have, like your two ants now, this side and this. These are optical, they are two mirror images, okay. If you bring them close to this side, they can overlap on themselves this way, okay. They are mirror images. So if you look at the right, you are seeing the left. Exactly what this functional group is, that's what this is. This functional group is the same now, but that is not the case in that place. So the only thing that changes there is the positioning of where the chlorine atom is, though still on carbon 1 and carbon 2, but the other one has been changed, the orientation has been changed up and down. So we say, because of that, the correct answer is option B, positional. Now, question 109. The basicity of tetraoxophosphate 5 acid is what? What is basicity? Basicity has to do with the number of replaceable hydrogen ion, okay, that is present in an acid, the number of replaceable hydrogen ion that is present in an acid. We could have the weak acid, we have the strong acid. If we dissociate them in water in solution, how many hydrogen can be replaced? If you are bringing in a metal to react with that acid to form salt, how many of the hydrogen ions can be replaced, can be replaceable? That's what we talk about in basicity. And when we talk about tetraoxophosphate 5 acid, tetraoxophosphate 5 acid, let's look at the board. Let's see the formula, because if you don't know the formula, you might have a challenge. Okay, PO4, yeah, this is tetraoxophosphate 5. Phosphate 5. Okay, so if we have in this case now, how are we sure? Is it 5? Oxygen is -2 times 4, that's -8. Okay, then this is plus 3 minus 8, that's -5. So if you move it to the other side, it is +5. So that's correct. So that is tetraoxophosphate 5 acid. So this is what it is. So if we dissociate this now, we're going to have ion. We have here 3 of that, okay, plus PO4, of course we have, because we have 3, this will be 3 minus at that point. So the number of hydrogen that can be replaced in this acid is actually 3. So the basicity is also 3. So let's look at the options. Option A, 1, option B is 4, option C is 2, and option D is 3. So the correct answer is option D. Do you know you can take practice questions on our simulated JAMB CBT past questions? All you need to do is to click on the link in the description below that takes you to the Myschool website. There, you'll be able to download the Myschool mobile app for your Androids and then the Myschool software on your laptops and computers. Please go ahead and start practicing. Now, let's move on to question number 110. Question 110. Which of the following is used in forming slag in the blast furnace for the extraction of iron? Which of the following is used in forming slag in the blast furnace? When we talk about slag, you know, there is an impurity, okay, in the extraction of iron. Usually, there's something we call slag. That slag is just an impurity, okay? When iron is being undergoing smelting, okay? When iron is being smelted, when it's undergoing smelting during the extraction of iron, what happens is that the iron is the major thing we need there, okay? But there are impurities because of where the iron, you know, ore was actually extracted from. So you will have some sand, okay, like silicon dioxide, SiO2 will be present there as impurities. Okay, so once it is subjected to heat, what happens? The iron will melt, okay, and then it's gotten, but you will now have the slag, the impurity, okay, that is formed on the surface of the iron that is melted, okay. But to now remove that slag, that impurity that is there, that silicon dioxide that is there, there's need to introduce a flux. A flux is what is going to remove that impurity, okay. Once we add that flux into it, that flux now attaches itself, and the flux that is poured in, introduced into the furnace, is calcium triosonitrate 5, that is CaCO3, okay, is what is attached. So once that happens, the calcium carbonate will now, you know, produce calcium oxide. Calcium oxide is what we actually need, okay. So calcium oxide will now react with the silicon dioxide to now form Ca2SiO4. Ca2SiO4. So that is going to be a slag. So you say, which of the following is used in forming slag, okay, in the blast furnace for the extraction of iron? So when we bring calcium carbonate into the furnace, what happens? It now produces CaO, that is calcium oxide, that eventually reacts with the silicon dioxide to form a calcium silicate, which is the slag that is removed from there. Then our iron is gotten. Let's look at the diagram and see how the process takes place. So you can see the diagram now. This is the process now. It has undergone, you know, smelting of the iron. So what we have here now that is being poured out at the slag, okay, you can see it very red, okay, in color because it's high temperature. Of course, the temperature that's melted silicon dioxide, sand, okay, is there with calcium carbonate to form this. So you can see now poured here. As it gets cooled, it turns like something like sand, okay. When you see it, it's like sand. So this is how it is. But once it gets cool, you can see it from here. What is formed here is Ca2SiO4. That's your calcium silicate that is formed here as our slag. So this is what happens here. So let's move back to the options we have. Okay, so which of the following is used in forming slag in the blast furnace for the extraction of iron? You have calcium. This is not correct because this is not the formula for calcium triisocarbonate 5, because CO3 actually has 2 minus and then calcium has 2 plus. So 2 we cancel out plus, so there should be no need for any 2 here. So it should just be CaCO3. So not this. This is your lime water. Okay, that's not what we need here because we need calcium oxide. So this is calcium carbonate, CaCO3. This is the correct answer. This one is technical because this is what we need. Actually, calcium oxide is what we need to react with the SiO2 to form the Ca2SiO4. But the question said which of the following is used in forming slag. So what we need is CaCO, but we will not get CaCO without getting CaCO2. So CaCO3 is actually what we need to get our CaO. Okay, so don't get it mixed up by saying, no, let me go for CaO that will react with SiO2 to give Ca2SiO4. This will be wrong. Okay, this is what we actually need. This is what we need to introduce into the furnace, the blast furnace of iron during the extraction of iron. Then this will now give us the CaO that we need, that will now give us. So the correct answer here is option C, calcium triisocarbonate 5. I hope you enjoyed this content. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video. Now on to question number 111. Calculate the number of moles of copper that will be deposited if 2 Faraday of electricity is passed through the copper during the electrolysis of copper 2 tetrazote sulfate 6. Okay, so first of all, we will need to write the reaction that takes place here. Okay, this is copper that is going to get deposited. Okay, so let's go to the board. So if we have copper here, copper ion, we have 2 plus, okay, 2 electrons, we gain here to eventually have copper metal. Okay, so once it loses 2 electrons, this that is here gives out 2 electrons, we have copper metals that is going to be formed. So which means that, don't forget that 1 Faraday should actually be equal to 1 mole of electron. Okay, 1 mole of electron. But in this case now, we have 2 electrons here. Okay, so that means that 2 is going to be multiplied by this Faraday. That's 2 electron times Faraday should give us 1 mole, okay, of copper. Okay, so 2 times that, that's it. In other words, we made 2F is equal to 1 mole, okay, that we are going to have there. So the question says that calculate the number of moles of copper that will be deposited. This is what happens based on this equation that we have written out. We have 2 Faraday should give us 1 mole. That is the ideal thing. But we are told that to calculate the number of moles of copper that will be deposited if 2 Faraday of electricity is passed through the copper. 2 Faraday of electricity. 2 Faraday of electricity is passed through the copper during the electrolysis of that. So we should find the number of moles. So if 2 Faraday is passed, we should find the number of mole, which is what? X mole. I think this does not need more stress. Okay, already 2 Faraday gives us 1 mole. So 2F gives us X. It also means 2F will give us 1 mole. But you can still do your calculation. If you cross multiply, we have 2 times X, we have 2X is equal to 2 times 1, that is 2. Okay, so you divide both sides by 2, of course we have 1. So which means X is equal to 1. So which means that the number of moles that is required for 2 Faraday to be produced in the electricity when passed through electricity is actually 1 mole. Okay, so let's go back to the screen. We have option A says 0.5 mole, option B 1.0 mole, 2.0 mole, and 3.0. So the correct answer is option B, 1.0 mole. Question 112. The volume occupied by 1 mole of an ideal gas at a temperature of 13 degrees Celsius and a pressure of 1.58 atm is what? We're given the constant, which is 0.082 atmospheric atm dm cube per Kelvin per mole. This question is what we call the ideal gas equation. Okay, while we're treating gas laws in one of our video lessons in chemistry, we dealt so much about this and we solved so many questions. So please do well to subscribe to our video lessons in chemistry so that you can have a good knowledge of this particular topic. So, but for the sake of this, we are going to just do justice to it now. The question says the volume occupied by 1 mole of an ideal gas. So we are going to write, let's move to the board. 1 mole of an ideal gas. So we can say number of moles is 1 mole. N represent 1 number of mole of an ideal gas at a temperature of 13 degrees Celsius. So we can write here T, temperature 13 degrees Celsius, okay? And then we're told, and a pressure of 1.58 atm. Pressure of 1.58 atm, okay, is what? Then we're given also R to be equal to 0.082. I will write the unit here because it's going to help us. atm dm cube per Kelvin per mole. Okay, per Kelvin per mole. Now, we're asked to find what? The volume. Okay, so we write that volume is question mark. That's what we want to find. So, with this will be able to help because we have written out the parameters we are given and then what you wish to find out. So, what you just need to do is look at the relationship between all these parameters. We have P here, we have V here, we have N here, we have R here, we have T. So, this, of course, we are already told that of an ideal gas. So, what is the formula for ideal gas equation? From what we have here, from ideal gas equation, PV is equal to nRT. PV is equal to nRT. We want to find the value for V. But before we go on to solve this, please ensure that you look at the unit of the constant, gas constant. It is very, very important because whatever unit that the gas, the gas constant is in, that is what the unit of all the parameters given here must be in. We have atm here for your pressure, we have dm cube here for your volume, so which means that your answer must be in dm cube. Take note, dm cube, and then we have per Kelvin here, which is your temperature. The temperature we're given is in degrees Celsius, so you must convert from degrees Celsius to Kelvin because the unit in this constant was Kelvin. So all we need to do, is to what? Changing from Celsius to Kelvin is by adding what? 273. If you had 273 here, you have 6 here, you have 7 plus 1, that is 8, and then we have 2 plus, that's 2. 286 Kelvin, okay? That's what we have. We've converted that, then we have per mole. So which means mole is already there. So we can move on now to slot in and substitute the values we have there. P, of course, is given as 1.58. I think we can just go ahead and divide since this is what we want to find the unknown. So divide both sides by P. Divide both sides by P so that P cancels P. So we say V is equal to nRT all over P. Okay, so our N is number of moles, which is 1 multiplied by R, okay, which is 0.082. Then multiplied by T, temperature is already 286, okay, Kelvin, all over. What is our pressure? The pressure was given to be 1.58. So by the time you solve all of this one and divide all of this one, we are going to have 14.84. 14.84 what? What's the unit? dm cube. dm cube. 14. The reason being that we had dm cube already here in the constant of R. So let's move on to the screen now and see what options we have. Option A says that 14.84 dm cube. Yes. Option B says 14.84 cm cube. Option D, some students will see this and then they will be thinking that it's the same thing. They are not the same thing. You must be very observant because the units are different. This is dm cube while this is cm cube, okay? So 14.84, even though they are the same, but the unit is actually in dm cube because the one we have in the constant is actually in dm cube. Option C says 0.64 dm cube and this says 0.64. So the correct answer here from what we got is 14.84 dm cube. Option A is the correct answer. Now question 113. If a salt weighs 2 grams and upon exposure to the atmosphere weighs 1.5 grams, this is as a result of what? What does it mean? Salt that was weighed, it was weighing 2 grams. So by the time you exposed it to atmosphere, to the atmosphere, you remove the cover and then it's exposed. What happened? You now took the weight again, the mass of the salt it now adds 1.5 grams. So which means there's a reduction in the mass. Okay, so what does that tell you? It tells us that there has been some quantity or amount of moisture, okay, or water that was actually in the soil that has what? That has evaporated, that has been lost due to what? Exposure to atmosphere. And the phenomenon of that, of what happens there, is what we call efflorescence. Efflorescence is a situation whereby, or is a phenomenon whereby a salt actually does what? Loses the water of the moisture content, and then once it's exposed to air, it loses the amount of air. So let's look at option A. It says that hygroscopy has to do with what? Absorption of moisture content. When you expose the salt, okay, if this mass was initially 2 grams, but when you expose it to atmosphere, okay, you now had 2.5 grams. So which means there's an increase in the weight of that particular salt. And then we were now told that maybe when it was done like that, what happened? It turned into what? Into solution. Okay, then we'll say that would have been hygroscopy. But in this case, that is not. There's a reduction in this. Option B says effervescence. Effervescence has to do with gases. Okay, when gases are evolved, we call that effervescence. They intentionally put these two here so that your code, two of them are EFF, so you get confused. Okay, so but if you don't know, effervescence has to do with what? Gases. When gases are given off, when you react calcium carbonate with HCl, for instance, and then there is CO2 that is given off, okay, that is what we call effervescence. Okay, but that is not what is happening here, because it is not gas that is being lost, it is moisture, water that is being what? That is being lost. Option C says efflorescence. Yes, efflorescence is a phenomenon where salt, when it is exposed to atmosphere, it loses its moisture content, or water of crystallization, it loses it, and then the mass or the weight actually reduces. So option C. Option D says deliquescence. Deliquescence is similar, is similar to hygroscopy, but the difference is that when this salt, okay, actually is exposed to atmosphere, it absorbs moisture, like in this case. But this one will just turn into what? Solution immediately. But this one will turn into, sticky. For instance, your sodium hydroxide pellet, if you open it and you expose your sodium hydroxide, what happens? It will absorb moisture and do what? It will turn into what? Into solution. So this one is, if it turns into solution, it means that it has absorbed more moisture, and then the weight should actually what? Increase than what it is. But this one, there's a decrease. So the correct answer is option C, efflorescence. Now, question number 114. Question 114. The compound of copper used as a fungicide or fungicide is called what? Option A say copper carbonate. Now, copper carbonate has a distinctive color, green color, okay, as its pigment. Okay, so as a result of that, this is used in the paint industry, in making of paints, okay, paint emulsion. So copper carbonate is not the compound that is used in fungicide. Okay, yeah, even though we have some other uses, but the major uses, okay, the major function of this copper carbonate is it is used in the paint industry. Copper nitrate is employed maybe in the organic chemistry, usually when you want to carry out a reaction that requires copper ion. Okay, so this is used as a source of copper ion in those chemical reactions. Okay, you need the copper ion, metal to react. So when you bring this one, you can get your copper from this. This is what this is used for. Yes, this also can be used for fungicide, but it is majorly because of how intense the chemical is, how corrosive it is, but it is not the major uses. Okay, where it is. Option C says copper sulfate. Copper sulfate is used in making algicide, okay, making fungicide, in fact insecticide, that are used in agriculture. What is it used for? Once there are algae, there are fungi that are affecting, or that are affecting the crops or the plants in agriculture, they just bring in copper sulfate to manufacture, or to treat those for, so that it can kill off the fungi and the algae that is present in agriculture. And option D says copper chloride. Copper chloride is used as a mordant, okay, in the textile industry where clothes are being made. This copper chloride is used. So the question says the compound of copper used as a fungicide, okay, is actually option C. Copper sulfate is what is used in killing or treating of fungi and algae in agriculture. So the correct answer is option C. Now let's move on to question 115. The percentage of hydrogen in the sixth member of the class of the aliphatic alkanes. Aliphatic is just meaning straight chain, okay, straight chain hydrocarbon, okay, alkanes is what? Hydrogen is this. So percentage of hydrogen in the sixth member of the class. So what's the sixth member of the class of alkane? Sixth members, that is C6H. Don't forget that alkanes has the formula CnH2n plus 2. Let's move on to the board. CnH2n plus 2, that's alkane, CnH2n plus 2. So which means that when n is equal to 6, because we are told sixth member, so that means C6H2 times, where n is 6, then plus 2 here. Okay, so this would be okay, that would be C6H2 times 6 is 12 plus 2, that's 14. So this is the sixth member of the aliphatic alkane family. So we're told to find the percentage of hydrogen in the sixth. So which means that percentage by mass of hydrogen, okay, in the compound will be equal to the mass of hydrogen itself. How many moles of hydrogen? We have 14 hydrogen there, 14. So we just say mass of 14 hydrogen, okay, all over the total mass of the entire compound itself, which is C6H14, okay, because we are finding the percentage, so that will be multiplied by 100, by 100, okay. So let's start with this. So the mass of 14 hydrogen, we can say mass of 14 hydrogen is equal to 14 moles, means 14 times, what is the mass of hydrogen? We're given to be 1, okay, so that will be 14, okay, we are done with that. Now the total mass of that, so we can find mass of C6H14 will be equal to, carbon actually is 12, we're given, that's the mass, times 6, okay, we have that, plus hydrogen still retains 1, then we have 14 of that, times 14, okay, so that gives us 12 times 6, that is 72, yeah, plus 1 times 14, that is 14. By the time you add up that, we have, that is 686, okay, so that gives us 80. So the total mass of C6H14 is 86. So the question now, to find the percentage mass of hydrogen will be equal to, back to this formula, mass of 14 moles of hydrogen is actually 14, so we have 14 all over. The mass of C6H14 is 86. Multiply that by 100. By the time you punch this on your calculator, you're going to have 16.28. Yeah, you can verify that. 16.28% is what we are. So the percentage, the mass of hydrogen in C6H12, the sixth member of the aliphatic alkane, is actually 16.28%. So let's move on to the screen. Option A is 41.34, 59. This, 16.2. So the correct answer is option C, 16.2. Now question number 116. Question 116. The law which states that a pure chemical compound, no matter how it is made, will be made up of the same elements contained in the same proportion by mass is what? Option A says law of conservation of masses. Law of conservation of masses states that masses or matter can neither be created nor destroyed, but can be transformed from one form to another. Looks like conservation, law of conservation of energy too, okay? So that is what it is. But this is saying that no matter how it is made, it will be made up of the same elements contained in the same proportion. Option B says that law of definite proportion. Law of definite proportion is saying that if you are going to get copper oxide, for instance, if you like, you can maybe dissociate copper nitrate to get copper oxide, or if you like, you can react copper with oxygen to form copper oxide. Or you can, maybe for your copper carbonate, maybe you can dissociate it to have copper, whatever formula that you can use, okay? The ratio of the ratio of the elements that make up that compound remains the same regardless of the route, regardless of the method you use in obtaining that. That is what the law of definite proportion, and which is exactly what states here, okay, though it is paraphrased. So the law which states that a pure chemical compound, no matter how it is made, will be made up of the same elements contained in the same proportion by mass. So that is the correct answer. Law of definite proportion. Option C says law of multiple proportion has to do with different proportion in which you can have a particular compound that is formed, okay, different proportion, and then you still have the percentage of what you have in that of the element that make up that particular compound. Option D says law of reciprocal proportion. So that's not, so the correct answer here is option B, the law of definite proportion. Question 117. The stability of atomic nucleus is determined by ratio of what? What determines? We are talking about the atomic nucleus, okay? The nucleus is present where? Don't forget that the nucleus is present at the center or the middle of the atom of an element, okay? And inside of that nucleus, what do we have? We have the neutron here, and then we have the protons present. Electrons usually are on the orbitals, on the shell, okay, revolving around the nucleus. So the major things that can determine the stability of atomic nucleus is determined by the ratio of what you have at the center or what you have inside of the nucleus, and that is what? Neutron, and then as well as what? Proton. So if the ratio of number of proton to number of neutron is the same, okay, so there is stability. If they have the same number, if one is more than the other one, there is instability. So the stability of atomic nucleus is determined by the ratio of neutron and electron. No, because this one has a charge of 0, okay, actually it's neutral, okay, and then this one is negatively charged. This one is at the outside of the electron revolving around on the shell. Option B is neutron and proton. Yes, ratio of neutron to proton, because both of them are what are present inside the nucleus, the atomic nucleus of an atom, okay? So this is correct. Option C says positron and neutron. Option D says electron and proton. No. If electron and proton, if you want to look at the stability of an atom, okay, how neutral an atom could be. Neutral an atom, not the atomic nucleus. Now, we are not talking about the nucleus. We are talking about the neutrality, okay, of the atom of an element. We'll be talking about electron and proton, because number of electron must be equal to number of proton. But we are talking about how stable is the atomic nucleus, the mass. What determines the mass of that is the proton and the neutron that is present in. So option B is the correct answer. The stability of atomic nucleus is determined by ratio of neutron to proton. The correct answer is option B. Now question number 118. 25 grams of potassium chloride were dissolved in 80 grams of distilled water at 30 degrees Celsius. Calculate the solubility of the solute in mole per dm cube. Calculate the solubility of the solute in mole per dm cube. It means that what amount of solute of the salt is dissolved in the particular quantity of the solvent at a particular temperature. Solubility is temperature dependent. Let's move on to the board and solve that question. We know that, okay, we're told that 25 grams of potassium chloride. So we have 25 grams of potassium chloride. So we can say that is the mass, okay, of the salt, potassium chloride. I will use the formula, that's KCl, was given to be 25 grams, okay? Then we're told that was dissolved in 80 grams of distilled water. So we can say 80 grams of distilled water. Water is in volume actually, but we're given mass. So it's the same thing. So we can say whether it's a mass of water or volume of water, okay? Volume of water, and don't forget that water is our what? Is our solvent, okay? That's what is dissolving the salt. So we can say volume of solvent, which is our water, is actually equal to 80 grams, okay, which is also equal to 80 cm cube, okay. Then we're told also that at the temperature of 30 degrees Celsius, at the temperature, I'll write this temperature of 30 degrees Celsius, calculate the solubility in mole per dm cube. Solubility in mole per dm cube. So question mark. That's what we want to find. So what is the formula now for solubility? Since we said it is the number of moles, okay, of a particular solute that dissolves in 1 dm cube of the particular solvent. So we say solubility is equal to number of moles of solute, that is your salt, which is the KCl, divided by, okay, let's just say number of moles of solute that dissolved in 1 dm cube. So that's why we have 1000 cm cube all over the volume of the solvent, okay, volume of the solvent, which is water. By default, it should have just been number of moles of solute that divided by the volume of solvent, okay, but because the solvent, usually the volume was given in gram, which is equal to cm cube, okay, and then it should be the number of moles that dissolve in 1 dm cube. So that's why we have the conversion, factor here, which is 1000. So that is always there. So number of moles of solute is equal to 1000 times this. So we want to find solubility. So the question is, were we given the number of moles of solute? No, but we can find the number of moles. Recall that number of moles, which is n, is equal to the mass, okay, over molar mass. Mass over molar mass. So if you solve that, we say that number of moles then will be equal to the mass of KCl was given as 25. So we can say 25 divided by, what is the molar mass of KCl? So we need to solve that. So we have here molar mass of KCl is equal to, we're given potassium to be 39 plus Cl is 35.5. That is atomic mass of that. So if by the time you sum the two together, that will be 0.5. 9 plus 5 is 4167. That is 74.5. This is gram per mole. Okay, that is the unit for that. So molar mass of that. So we have 25 divided by 74.5. Okay, this is going to give us the number of moles of this solute. So we can just plug in this into this so that we have solubility will be equal to number of moles now is 25 over this, the whole of this. So that will be 25 over 74.5. That is our number of moles, okay, multiplied by 1000, divided by volume of solvent, which is water, was given as 80 gram, which is 80 cm cube, divided by 80. So by the time you solve this and then you punch your calculator, you'll be going to have 4.2, of course, 0 mole per dm cube. 4.20 mole per. You can punch your calculator to verify this and check if the answer is correct. So the solubility of that salt is K 4.2 mole per dm cube. Let's look at the screen. Option A 3.9, 4.6, 4.0, 4.2. So the correct answer is option D, 4.2 mole per dm cube. Question number 119. An example of a physical change is, don't forget, physical change has to do with a change where no new substance is formed, okay? The composition remains the same. Even if the product is formed, okay, you can still form back what you have initially. For instance, if you freeze water, okay, it turns to ice block, okay. If you get the ice block, you bring it out again and reduce the temperature, increase the temperature, what happens? The ice block is going to what? It's going to melt and then go back to the water you formed back. So that is a physical change because you can get that back. But chemical change, if you get firewood now, let's say with the wood now, you set it ablaze, you put fire and then it burns into ashes and charcoal. If you get the ashes, you get the charcoal, at the end of the day, if you bring them together back, you cannot get the firewood you burnt from the beginning. So that is an example of a chemical change. So the examples we have here, say an example of physical change is what? So which means every other one, 3 of them will be chemical change, but 1 of them is physical change. Option A says slaking of lime. If you slake a lime, it's a chemical reaction, okay? You will get, the product you are going to get will be a new substance, and the composition of the mixture, of course, will change from what it was initially. So this is a chemical change, okay? this is a chemical change, okay, that we have. This one, liquefaction of liquids. Liquefaction of liquids is a physical change. It's a physical. I will explain the reason. The reason being that what happens is that gas is turned into liquid in liquefaction of liquids. So once the gas is turned into liquids, the composition of that liquid does not change, of the gas does not change from what it was originally. Okay, the composition is retained. The only thing that happens is that what, peradventure, maybe the pressure was increased. So once you increase the pressure, the sediments of the gas will begin to what, to form closer, bring them closer to themselves. They bring closer together, and then they begin to act and form what, fluid, that is liquid. Okay, so but the composition of that gas still remains the same thing as it was even when it became what, liquid. So you can get what you had back, and then you get back. So liquefaction of liquids is actually what, an example of physical change. The same thing, if you decrease the temperature of it, what happens? The same thing happens. You are going to have that. So an example of physical change is liquefaction of liquid. Option C says dissolution of limestone in acid. If you get your calcium carbonate limestone, pour in your HCl into it, it will dissolve, and then what happens? There will be effervescence because CO2 is going to be given off, okay, and then you have calcium oxide left here. CO2 is given off. You cannot get the CO2 and then bring it back to react with a CaO, and then you get calcium carbonate back. No, once it's dissolved, and then your HCl is dissolved. So that is a chemical reaction because a new substance is formed. Option D says rusting of iron. If your iron gets rusted because you have had it, if your iron, is rust, you had what's it called? Because in the presence of oxygen, air is exposed to air, and then moisture comes in. You have Fe2O3.XH2O. So once you have that, that is your rust. So what happens? You cannot get back the original iron that you had back. Even no matter how you try to maintain, the oxygen cannot be taken away, the moisture cannot be taken away. A new substance is formed. So because of that, an example of a physical change is liquefaction of liquids. So the correct answer is option B. Question number 120. Question 120. The product formed when ethyne is passed through a hot tube containing finely divided iron is what? This reaction is what we call the cyclic polymerization. Polymerization has to do with the combination of your combining together of two or more monomers. Okay, we have smaller units of hydrocarbons that are blended together to form a larger desired one. So to form aromatic, what happens is that ethyne, we have 3 moles of ethyne will undergo polymerization, cyclic polymerization, to be able to give us what we call benzene. Let's look at the reaction that takes place here. We have ethyne. Don't forget, ethyne is C2H2, okay? That's your alkyne family. We have 3 of that, okay? One of these plus another one in cyclic form, okay? Then we are going to have C6H6. Don't forget, it is in presence of what? Finely divided what? Iron, okay? You have iron there. Okay, of course, in the presence of. So by the time you do this, what happens? We have C6H6. This is 6. This is 6. And this is what we call benzene. And don't forget, benzene is an aromatic compound. Aromatic in the sense that it has what we call conjugates. Okay, we call it conjugated bonds. We have aromatic. We have a single bond, a double bond, alternating single bond, double bond. If you draw the structure of this benzene ring, we have double bond, single bond, double bond, single bond, double bond. Okay, so this is aromatic. Okay, so benzene is an example of aromatic. So the question says again, let's move back to the screen. The product formed when ethyne is passed through a hot tube containing finely divided iron is not polymeric, saturated, it's not saturated, it's hydrated, and then we have aromatic. Benzene is what is formed, okay, from cyclic polymerization of ethyne. So benzene is aromatic. So the correct answer is option D. Do you have any question bothering you at all from all we've done so far? Please feel free to ask your question. All you need to do is to go to the link in the description below that takes you to the Myschool website. There you'll be able to ask your questions, and solutions will be provided within the shortest period of time. Now let's move on to question number 121. H2S reacts with chlorine, that's chloride gas, that's chlorine gas, Cl2, and then we have 2 moles of HCl gaseous, so that means hydrogen chloride, okay? plus sulfur. Okay, so what is the change in oxidation state of sulfur from reactant to product? Sulfur from reactant, so we look at what sulfur is here. This is where we have sulfur, then we have sulfur here. So we want to calculate the oxidation state from this to this. Already this is 0 because the oxidation state of a free element, of an element, atom of an at the free state is 0. So this, we know this one as 0. So what we want to do now is to calculate for this one. So let's move on to the board now. We are looking at H2S. Oxidation state, the reaction is between H2S and chlorine gas to give us HCl, 2 moles of that, plus sulfur. Okay, so we already know that the oxidation state of this is 0. So for this one now, H2S, oxidation state of H2S, this is a compound we equate it to be 0. Hydrogen we know to be plus 1, so we have plus 1 times 2 of that times 2, then plus sulfur equal to 0. So 1 times 2, that is 2 plus S equal to 0. So S is equals to -2. So that means there's a change in oxidation state from -2 to this sulfur here is 0, okay? Because this, the atom of an element that is in a free state is equal to 0. So from -2 to 0. Let's move on to the screen. -2 to 0. Option B, A, B, C. So option C is -2 to 0. So the correct answer is option C. The correct answer is option C, -2 to 0. Do you have better steps or solutions to some of these questions or these questions that we have solved? Please feel free to share with us. You can do that by simply going to the comment section. You indicate the question number and the solution you would like to share. Question number 122. If a stable neutral atom has a mass number of 31, the number of electrons and neutrons respectively are, we were just given the mass number to be 31. Well, if you are smart enough to know the mass number of the element, usually what I do is I'll just divide this by 2, okay? In most cases, to give me an idea. If I divide this by 2, what I have will be closer, if not exactly, the element that actually the atomic number. So if I divide 31 by 2, that would be around 15.5, okay? So 15.5 is not it's not an atomic number, so but of elements in periodic table, but we can have 15. Okay, so what element is 15? So that will give me an idea. So if we have 15 as the atomic number of that element, for instance, it means that that element will have number of protons will be 15, and the number of electrons will also be 15. The number of proton of neutron will be different, because if mass number is 31, mass number, don't forget, mass number is number of proton plus neutron. Okay, so if number of proton is already 15, subtract 15 from 31, you will get 16. So which is what? 15, 16 will give us that. So that means it should be number of electron comes first before neutron. So electron should be number of proton, which is 15, while neutron will be 16. 15 and 16. 15 and 16, so which is option A. Or on the other hand, alternatively, you can use the elimination method. We have 31 as the mass number, okay? So which means that number of electron must be equal to number of proton, and number of proton plus number of neutron must be equal to 31. So sum up the two answers you have. If it gives you 31, then you can leave. If it does not give you 31 or gives you more, you eliminate. Option A says 15 and 16. 15 plus 16 will give us 31, okay? So this one, we can leave this. Option B, 16 plus 31 will be more than 31. So this one is eliminated. 15 plus 31 will be more than this, so this is eliminated. 16 and 15. 16 plus 15 will also give us 31. So this is left. So elimination method eliminates B and option C. So we are left with option A and option B. And then we're told that we have to find the number of electrons and number of protons respectively. So which means the first value that comes must be electron, the second that comes must be what? Must be neutron. And it is not possible for number of electrons to be more than number of neutron. It is not possible. You cannot have number of electrons more than number of neutrons. You can have number of neutrons to be equal, okay, to number of electrons if number of proton is also equal. Like we have 16 oxygen and 8 oxygen, 16 mass and oxygen. So number of electron is 8, number of proton is 8, number of neutron is 8. But you cannot have the value of number of electron bigger or a greater than number of s. So in that case now, the first value that comes will be for electron, and then 16 will be for number of neutrons. So the correct answer with the two methods we have shown now shows clearly that the correct answer is option A. Question number 123. Scandium is not regarded as a transition metal because its ion has what? Remember, transition metals are metals or elements that have partially filled d orbital. Okay, the d orbitals of shell are partially filled, not fully filled, not completely filled, partially filled. Okay, and usually we have from the first series of transition metals are elements from 21 to 30, where we have from scandium ranging to 31. But in most cases, scandium is not regarded as a transition metal. Okay, and then the last one, which is zinc, also is not regarded because zinc has completely filled d orbital shell, and the definition for transition metal is that what? They must have partially filled d orbital. Now, scandium is not regarded as transition metal because there is no electron in the d orbital. Well, if you write the electronic configuration of this scandium, of course, it is 21. So which means you have 1s2, 2s2, all the ones you have. Let's look at the board. So you can have that scandium is having atomic number of 21. So that will be 1s2, 2s2, 2p6, 3s2, 3p6. Okay, 4s2. Let's count. You are going to 21. 2 plus this, that's 4, 10, 2, 2, 2. That's 20. So just one left. So we have 3d1. Okay, 3d1. Okay, so usually we put the d first, then the 4, because in energy level, so we have 3d1, 4s2. Okay, so now what happens is this is the electronic configuration of scandium having 21. But now when this scandium goes through a reaction, okay, usually it will lose 3 electrons. 3 electrons will be lost. That's why we write it as this. Scandium has a valency of +3. Okay, now once it loses 3 electrons, what happens? It loses out this. It's going to lose 3 electrons. So it will lose this 1 electron in the 3d, and then loses also this 2 electron in the 4s. So 2 plus 1 makes 3. So by the time it loses this one, the ionic state, or yes, the ionic state of scandium is no longer going to have this 3d, because it has lost this 3 plus means it has lost 3 electrons, and the 3 electrons in order of arrangement is going to be 1 from this 3d orbital, and then this, so it has lost the d orbital that qualifies any elements to be a transition metal. So because of that, what we'll be having now for 3 plus of scandium is all of this, of course. Okay, which is your argon. Okay, I think that's your argon. Yeah. Okay, argon, the isomerical argon, that's what you are going to have eventually. So it has lost this. So because it's losing this, it does not have any d orbital, no electron in the d orbital any longer. Let's move on to the screen now. So scandium is not regarded as a transition metal because its ion has no electron in the d orbital. Yes, ion, that means Sc3+. Option A is correct. Option B, a partially filled d orbitals. No, it's ion. Okay, once it's ion, it does not have d orbital again, so it's not. But if it is the neutral scandium atom has partially filled d orbital. It has 3d1, but the ion has no. So this one is wrong. Option B is wrong. Okay, option C say a completely filled 4s orbital. That's not it, because that is not what qualifies any element for transition metal. Partially filled d orbital, and option D say a partially filled 4s orbital. No, it should be 3d orbital. So the correct answer is option A. No electron in the d orbital. Question 124. 1 to 4. Question 124. An example of highly unsaturated hydrocarbon is, remember that unsaturated hydrocarbons, we have the hydrocarbons we have the alkane, we have alkene, and we have alkyne. Okay, alkenes, that's ALKNES, okay, which has general formula of CnH2n plus 2, are referred to as saturated hydrocarbon because they have carbon-carbon single bond. Okay, between them, carbon-carbon single bond is what we have. Carbon-carbon single bond for alkane. Okay, but the alkene and the alkynes are the unsaturated hydrocarbon. The alkenes has double bond carbon-carbon, and the alkynes have triple bond carbon-carbon triple bond. Okay, so these are saturated. the remaining two, alkene and alkynes, are unsaturated. But the question says an example of highly unsaturated. So which means between these two, this is saturated, this is unsaturated, this is also unsaturated. Alkenes are unsaturated, alkynes are also unsaturated. But the one that is highly, that will be more unsaturated, is the one that has carbon-carbon triple bond, which is this. So alkynes usually will be highly unsaturated than alkenes. So if you look at the options we have C2H2. Okay, C2H2 is that's alkyne, of course. That's your acetylene, or that's your ethene. Okay, that's what option A is. So this is an alkyne, okay, which is highly triple bond. We have carbon-carbon triple bond. If you draw that, we have C triple bond C and H. So there's carbon-carbon triple bond. CH4, that's methane. That's your methane. That's, of course, that is an alkane. So this one is saturated hydrocarbon. Then we have C2H4. That is your ethene. Ethene is unsaturated hydrocarbon, but it's carbon-carbon double bond. So which means it is less unsaturated compared to this. And then we have C4H10. C4H10 is your butane. Butane is also a saturated hydrocarbon like this. So B and D is knocked off from the option is eliminated. We have option A and C left. Both of them are unsaturated hydrocarbon, but option A, ethene or acetylene, is more or highly unsaturated compared to the ethene. So the correct answer is option A. Question number 125. Biodegradable pollutants are not safe in water systems because they can cause what? Don't forget, biodegradable pollutants, from the word bio means life. Okay, when we have living organisms like microorganisms acting, ability to break down some compounds, okay, organic compounds, okay, that are pollutants, is what we call biodegradable pollutant. But because even though they can be, they can be split or they can be broken down by microorganisms or by bacteria, okay, on that, when they get into the streams of water, they are still harmful because we still have those microorganisms still present there. Some of those chemicals that have been broken down still moves into the water. Don't forget, it says that which one of these pollutants, okay, biodegradable pollutants, are not safe in water system. They are not safe. Even though they have been broken down by bacteria and microorganisms, they are still not safe when they get into the water because they can cause death of those microorganisms, of the fishes that we have there. Fish kill, what we call fish kill. The animals therein begin to die because once they get in there, they can no longer, they are pollutants, okay? They will cause the health, the death of those organisms that are in the option A says air pollutants. Of course, air pollutant has nothing to do with what the water system. So option A is not. Option B says soil degradation. Where we are talking about water pollutants here. We are talking about something that is more. Yes, they will call soil degradation. Yes, even though they have been broken down. But do not forget that there is one that is more. Water systems, organisms live in there, and then some feed, respirate, some excrete with that inside that water. They need oxygen, dissolved oxygen, to be able to respire and live. So soil degradation is not. Then we have option C, says ill health. Ill health is more than the soil degradation. Ill health, of course, when organisms begin to die, the fishes therein, both animals and the plants that need the pollutants get in there, they affect the health of those organisms, and then they cause, they constitute nuisance to them, and then they cause harm to them. So it will cause ill health because they can cause ill health. This is correct. Option D says greenhouse effect. Greenhouse effect is felt usually in the atmosphere, okay? Ozone layer depletion will lead to, when we have gases, those gases begin to react there, they will cause the ozone layer depletion, then we can have greenhouse effect. But we are talking about water system on the ground when they are broken. So the correct answer here is option C, ill health. I believe you enjoyed this content because I really did. If yes, don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video.